Was there a beginning of time?
Imaginary time is like another direction in space.
What is gravity and how does it work?
Imaginary time. People think it's something you have in dreams, or when you're up against a deadline. But it's a well-defined concept.
How do stars eventually run out of fuel and die?
The boundary condition of the universe is that it has no boundary. Nothing was around before the Big Bang. According to Einstein's general theory of relativity, space and time together form a space-time continuum.
How do general relativity and quantum physics conflict with each other? This is a brief history of time by Stephen Hawking.
5, 4, 3, 2, 1.
The theories of relativity and gravity are probably familiar to you. However, have you ever stopped to consider what we actually mean when we refer to theories? A theory is a model that adequately explains significant groups of observations, to put it simply. Scientists gather information from observations they make during experiments, for instance, and use it to create theories that explain how and why phenomena occur. For example, Isaac Newton developed the theory of gravity after observing many phenomena, from apples falling from trees to the movements of planets. Using the data he collected, he was able to describe gravity in a theory. Theories have two great benefits. First, they allow scientists to make definite predictions about future events. Newton's theory of gravity, for instance, made it possible for scientists to predict the future motions of celestial bodies like planets. With the aid of the theory of gravity, it is possible to predict something as specific as where Mars will be in 6 months. Second, theories are always disprovable, meaning they're open to reform if new evidence that doesn't fit the theory is found. For instance, the idea that the Earth is the center of the universe was once widely accepted. Galileo disproved this theory when he noticed moons orbit Jupiter. He could therefore show that actually not everything orbits the Earth. In effect, no matter how reliable a theory appears at the time, a single future observation can always invalidate it. This means that theories can never be proven correct, and science is a constantly evolving process. Before Isaac Newton, people believed that an object's natural state was complete rest. This indicates that the object would remain motionless in the absence of any external force. Newton thoroughly disproved this long-held belief in the 1600s. In its place, he proposed a theory stating that all objects in the universe, rather than being still, were in constant motion. Newton determined this through his discovery that the planets and stars in the universe were constantly moving in relation to each other. For example, the Earth is constantly orbiting the Sun, and the entire solar system is rotating around the galaxy. Therefore, nothing is ever still. To describe how all objects in the universe move, Newton developed 3 laws. The first of Newton's laws states that if no other force acts on an object, it will continue to move in a straight line. Galileo demonstrated this in an experiment in which he rolled balls down a slope. The balls rolled in a straight line because gravity was the only force acting on them. According to Newton's second law, an object will accelerate at a rate proportional to the force acting on it. A car with a more powerful engine, for example, will accelerate faster than one with a less powerful engine. According to this law, the greater a body's mass, the less a force affects its motion. For example, if 2 cars share the same engine, the heavier vehicle will take longer to accelerate. The third law of Newton describes gravity. It says that every object in the universe attracts every other object with a force that is proportional to its mass. This means that if the mass of an object is doubled, the force will also be doubled. If you double one object's mass and triple the other, the force will be 6 times as great. As we've seen, Newton's theory eliminated absolute rest in favour of the notion that an object's movement is relative to that of other objects. However, the theory also implied that an object's speed is relative. Imagine that you are reading a book while riding a train at 100 miles per hour. How quickly are you moving? To an observer watching the train pass, you are travelling at 100 miles per hour, but to you, your speed is 0 miles per hour. Therefore, your velocity is relative to another object. Yet one major hole developed in Newton's theory: the speed of light. In contrast to relativity, the speed of light is constant. It moves at 186,000 miles per second. The speed of light doesn't change regardless of how fast other things are moving. For example, if that train was travelling at 100 miles per hour towards a beam of light, the speed of light would be 186,000 miles per second. Even if the train came to a complete stop at a red light, the light beam would still be travelling at 186,000 miles per second. The speed of the light remains constant regardless of who is viewing it or how fast they are travelling. This fact causes problems for Newton's theory. How can the speed of something be constant, regardless of the state of the observer? The answer was discovered in the early 20th century when Albert Einstein postulated his theory of relativity. The constant speed of light was problematic for Newton's theory because it demonstrated that speed was not always relative. As a result, scientists required an updated model that accounted for the speed of light. Albert Einstein developed such a theory, the theory of relativity. According to relativity theory, the laws of science apply to all freely moving observers. This means that no matter how fast someone is, they will experience the same speed of light. This may appear straightforward at first glance, but one of its central suggestions is actually very difficult for many people to grasp. Time is relative. Because the speed of light does not change for observers moving at different speeds, observers traveling at different speeds would actually measure different times for the same event. For example, suppose a flash of light is sent out to 2 observers, one traveling towards the light and the other traveling faster in the opposite direction. Even though they are traveling at different speeds and in opposite directions, the speed of light would be the same for both observers. This would imply that they each experience the flash event as if it occurred at 2 different times. This is because time is calculated by dividing the distance traveled by the speed of an object. The speed of light is the same for both observers, but because the distance between them differs, time is relative to each observer. If both observers carried clocks to record when the light pulse was emitted, they would confirm 2 different times for the same event. Who's right? Neither. Time is relative and unique to both observers. Particles like photons or electrons make up all matter. Scientists aim to measure them and examine their speed to learn more about the universe. However, when you try to analyze particles, they behave in a very peculiar way. Strangely, the more accurately you try to measure a particle's position, the less certain it is, and the more accurately you measure a particle's speed, the less certain the position is. The uncertainty principle is the term used to describe this phenomena, which was originally observed in the 1920s. Scientists had to employ other methods of observing particles due to the uncertainty principle. Therefore, they started focusing on a particle's quantum state. A particle's quantum state combines all of its likely potential locations and speeds. Since it is impossible to determine a particle's precise position or speed, scientists consider all of the possible positions and speeds that a particle could have. The likelihood of each potential location where a particle might be is calculated as it moves around. To help them determine this, scientists treat particles as if they are waves. Because a particle can be in so many various places, they seem to be a continuous succession of oscillating waves. Imagine a string that is pulsating. The string will arc and dip through peaks and troughs as it vibrates. A particle also behaves like this, although its possible path is a series of such overlapping waves, all happening at once. By examining particles in this way, researchers can determine the particle's most likely location. The arcs and dips on the various waves must coincide for the particle to be in one of its most likely places, and they must not coincide for it to be in one of its least likely positions. This is called interference, and it shows which positions and speeds are most probable for the particle wave's path. You are perceiving the world in 3 dimensions, which allows you to categorize every object based on its height, width, and depth. Although we cannot see it, there is a 4th dimension that joins the other 3 to form spacetime, which we refer to as time. This 4-dimensional spacetime model is used by scientists to explain cosmic phenomena. An event is something that takes place at a specific time and place in space. Therefore, in addition to the 3-dimensional coordinates, a 4th coordinate representing time is included when calculating an event's position. Scientists have to take time into consideration when determining the position of an event, because the theory of relativity states that time is relative. It is therefore an important factor in describing the nature of an event. An amazing consequence of the combination of space and time is how it changed our conception of gravity. Massive things bend space-time, causing gravity. A massive body, like the Sun, can literally bend space-time. Consider it like this. Think of space-time as a blanket that is held in the air and being spread out. The blanket will curl, and the object will slightly sink if you place it in the center of the blanket. Massive things alter space-time in ways similar to this. Then other objects travel along these space-time curves. This is due to the fact that an object will always choose the route that will carry it from point A to point B, which is a circular orbit around a larger object. If you take another look at that blanket, you will notice this. A smaller marble, for example, will follow the larger marble's indentation if you place a large object, like an orange, on the blanket, and then try to roll a smaller one past it. The same principles apply to gravity. Stars require vast amounts of energy to generate heat and light throughout their lifetimes. However, this energy eventually exhausts itself, causing the star to die. Depending on its size, a star's death has different effects. A black hole is produced when a very massive star exhausts all of its energy. The gravitational field of the majority of big stars is so intense that it creates black holes. The star can use its energy to prevent collapse while it is still alive. But when a star runs out of fuel, it is unable to defy gravity, and its deteriorating body collapses in on itself. Everything is pulled inwards toward an infinitely dense, spherical point called a singularity. This singularity is the black hole. When a black hole forms, spacetime is curved so steeply by its gravity that even light bends along it. In addition to devouring everything in its vicinity, black holes also create a point of no return across which nothing can pass. Even light, which travels faster than anything else in the universe, cannot cross this point, which are called event horizon. This raises a question. If a black hole absorbs light and anything else that crosses its event horizon, how can we know they are there? Scientists search for black holes by looking for their gravitational effect on the universe and for the X-rays produced by their interaction with orbiting stars. For example, scientists look for stars orbiting dark and massive objects that could be black holes. They also look for the X-rays and other waves that are commonly produced by matter when it is being sucked in and torn up by a black hole. There is even a source of radio and infrared waves at the center of our galaxy that could be a supermassive black hole. If the gravitational pull of a black hole is so strong that not even light can escape it, then you'd think nothing else could escape either. But you'd be wrong. In fact, black holes must release something. Otherwise, they'd break the second law of thermodynamics. According to the second universal law of thermodynamics, entropy, the tendency towards increased disorder always increases, and as entropy increases, temperature must also rise. An example of this is how a fire poker shines red hot and emits radiation as heat after being in a fire. Since black holes absorb disordered energy from the universe in accordance with the second law of thermodynamics, the entropy of the black hole should also increase. In addition, as a result of this increase in entropy, black holes should have to let heat escape. Although nothing that has passed a black hole's event horizon can escape, virtual pairs of particles and antiparticles near the event horizon conserve the second law of thermodynamics, allowing for the escape of heat. Virtual particles are particles whose effects can be measured but which cannot be detected. One of the companions has positive energy, while the other has negative energy. In a black hole, gravitation is so powerful that it can pull the negative particle into the black hole, releasing enough energy for the positive particle's partner to potentially escape into the universe and emit heat. Thus, the black hole is able to emit radiation in accordance with the second law of thermodynamics. Negative particles being sucked into the black hole are equal to the quantity of positive radiation emitted. This inward flux of negative particles can reduce the mass of the black hole until it evaporates and dies. And if its mass is sufficiently reduced, the black hole will likely end in a final explosion as powerful as millions of H-bombs. A situation where the universe shrinks and time reverses. How would that play out? Maybe clocks tick in reverse and history goes back. While scientists haven't totally dismissed it, 3 compelling clues point to time moving only forward. The first indication that time flows from past to future is the thermodynamic arrow of time. According to the second law of thermodynamics, entropy, or the disorder within a closed system, tends to increase over time. This implies that time's passage can be tracked by the natural tendency of disorder to grow. For instance, consider a cup falling from a table and shattering. This event leads to decreased order and higher entropy. The fact that a shattered cup won't magically reassemble and become more orderly shows that time only progresses in one direction. The broken cup and the thermodynamic arrow of time also relate to the second indicator of forward time, the psychological arrow guided by memory. Once the cup has broken, you can remember it being on the table, but before it fell, when it was still on the table, you can't recall its future position on the floor. The third indicator, known as the cosmological arrow of time, relates to the expansion of the universe, aligning with our perception of the thermodynamic arrow. As the universe expands, entropy increases. If disorder in the universe were to reach its maximum, the universe might begin contracting, reversing the cosmological arrow of time. However, we would be unaware of this reversal, because intelligent life can only exist as disorder increases. This is due to our reliance on entropy to break down food into usable energy. Therefore, as long as we're around, we will observe the cosmological arrow of time as going forward. What kinds of forces are at work in the universe? Most people are familiar with only one force: gravity, the force that attracts objects to each other, experienced as Earth's gravity pulling us toward its surface. However, most people are unaware that there are actually 3 additional forces that act on the smallest particles. The first is the electromagnetic force, visible in daily life when a magnet sticks to a refrigerator or when you charge your phone. It acts on all particles with electric charges, like electrons and quarks. The electromagnetic force, similar to the attraction and repulsion between the north and south poles of a magnet, can either attract or repel. Positively charged particles attract negative ones and repel other positive particles, and vice versa. This force is significantly stronger than gravity and is dominant at the atomic level. For instance, the electromagnetic force causes an electron to orbit around an atom's nucleus. The second force is the weak nuclear force, which acts on the particles that compose matter and is responsible for radioactivity. It is termed weak because the particles that carry it can only exert force over very short distances. At higher energies, the strength of weak nuclear force increases until it matches that of electromagnetic force. The third is the strong nuclear force, which holds protons and neutrons together in an atom's nucleus and binds the smaller quarks within them. Unlike the electromagnetic and weak nuclear forces, the strong nuclear force weakens at higher energies. At a very high energy level known as grand unification energy, the electromagnetic force and weak nuclear force become stronger, while the strong nuclear force weakens. At this point, all 3 forces achieve equal strength and manifest as different aspects of a single force, which may have played a role in the creation of the universe. Most scientists believe time began with the Big Bang, when the universe transitioned from an infinitely dense state to its current rapid expansion. Scientists, however, don't exactly know how this Big Bang occurred, although a number of theories have been proposed to explain how this huge expansion might have happened. The most widely accepted theory of the universe's beginning is the hot Big Bang model. In this model, the universe originated from a point of zero size that was infinitely hot and dense. During the Big Bang, it expanded and cooled as its heat dispersed. Most of the elements present in the universe today were formed within the first few hours of this expansion. As the universe continued to expand, gravity caused denser regions of the expanding matter to start rotating, creating galaxies. Within these newly forming galaxies, clouds of hydrogen and helium gases collapsed. Their colliding atoms caused nuclear fusion reactions, which created stars. When these stars later died and collapsed, they created huge stellar explosions that ejected more elements into the universe. This provided the material for the birth of new stars and planets. Although this is the generally accepted version of the Big Bang and the birth of time, it's not the only model. Another model is the inflationary model, which suggests that the early universe's energy was so extraordinarily high that the strengths of the strong nuclear force, weak nuclear force, and electromagnetic force were equal. However, as the universe expanded, the three forces quickly assumed different strengths. When they separated, a tremendous amount of energy was released, resulting in an anti-gravitational effect that caused the universe to expand rapidly and at an increasing rate. In their quest to understand and explain the universe, scientists have developed two major theories. The first is general relativity, which focuses on a large-scale phenomenon, gravity. The second is quantum physics, which examines some of the smallest known entities in the universe, subatomic particles. Although both theories offer significant insights, there are considerable differences between the predictions made by quantum physics equations and those made and observed in general relativity. As a result, there is currently no method to combine them into a single unified theory of everything. One challenge in merging the two theories is that many equations in quantum physics yield seemingly impossible infinite values. For instance, the equations suggest that the curvature of spacetime would be infinite, which observations have proven to be incorrect. To eliminate these infinities, scientists attempt to introduce additional infinities into the equations. Unfortunately, this hinders accurate predictions. As a result, rather than using quantum physics equations to predict events, scientists must adjust the equations to fit the observed events. A second similar problem is that quantum theory suggests that all the empty space in the universe is made up of virtual pairs of particles and antiparticles. However, the existence of these virtual pairs causes difficulties for general relativity. Since there is an infinite amount of empty space in the universe, the energy of these pairs would have to have infinite energy. This poses a problem because Einstein's well-known equation E equals mc squared indicates that an object's mass is equivalent to its energy. Therefore, if these virtual particles possess infinite energy, they would also have infinite mass. An infinite mass would lead to the entire universe collapsing under its immense gravitational pull, resulting in a single black hole.
It does. It's what raises us from being cavemen. On one view, we're just weak, feeble creatures at the mercy of the forces of nature. When we discover the laws which govern these forces, we rise above them and become masters of the universe.
I become a master of the universe.